Good morning, everyone. Last time, while I was explaining chapter 20, I have arrived till this slide. I have explained the atomicity adiabatic constant. I will remind you what did I explain. So let's go back through the presentation to just revise what did I explain. So first of all, for sure, our chapter was about the first law of thermodynamics. We have tried to find this first law. I've started by defining what is a thermodynamical process. I've talked about a cyclic process. I've distinguished between reversible and irreversible process. So remember that through all our problems, we will be talking about only reversible processes, and a reversible process is a process that takes place very slowly. Okay, so that I can have a thermal equilibrium between each instant and the other. So I have distinguished 4 types of reversible processes, which are important processes that we're going to study them during our exercises, which are the isothermal process. It takes place at constant temperature. Adiabatic process, it takes place without any exchange of heat. Isobaric process, it takes place at a constant pressure, and isochoric process, it takes place at constant volume. Okay, these are the common processes that we are going to study during our through the whole part of thermodynamics. We will more be interested in ideal gases. Ideal gases have a very important equation, which is called the equation of state of an ideal gas. It's given by PV equals nRT, where P is the pressure, V is the volume, and number of moles, R is a constant. It's called the ideal gas constant. It's equal to 8.314. And T is the temperature in Kelvin. It's called the absolute temperature. It's never in degrees Celsius. So you have to keep this into your considerations. Now I've explained the work done by the gas and not to the work done on the gas. The work done by a gas, it's equal to integral PdV, or dW, it's equal to PdV. So the whole work, it's equal to integral PdV. So this is the work done by the gas or by the fluid. We all know that if volume is increasing, we have a positive work, so the gas is doing work. Bainama if the volume is decreasing, so dV will be negative, so the work will be done on the system or on the gas. That means the work done by the gas is negative, so the work done on the gas is positive in this way. If I'm drawing a PV diagram, as I have already explained, دايما الانتجرال PdV depends on the starting point and the ending point. It depends, I'm starting from what volume till what volume I'm reaching. So you can see that if I'm going from a small to large volumes, I'm expanding, and in this case the work is equal to the area under the curve, because integral PdV, it's similar to mathematical problems where integral fx dx is equal to the area under the curve f of x. So here it's the same, but instead of y we have p, instead of x we have v. So it's integral PdV. This is the area under the curve in the PV diagram. So if we have an expansion, as in figure A, I'm going from point 1 to point 2. So the work done by the gas, it's equal to integral PdV. It's equal to the area, because simply the area is equal to the integral PdV from V1 till V2, from small values till large values. Now the work in the second case, we have a compression. You can see that V1 is larger than V2, so I have compression. In this case, the work done by the gas must be negative, because the work, which is integral from V1 to V2 PdV, is negative simply because V1 is larger than V2. So if you're making an integral from large to small values, you will get a negative sign. So it's equal to minus area under the curve. Okay, it's equal to minus area. Here in the figure they have written area. It's in reality it's minus area under the curve. We have learned how to find the work in different processes, because you are going to deal with these processes: isobaric, isochoric, isothermal. So each one has its own formula. You can revise them. Okay, you must know how to derive them. Okay, but when you solve, you can just write the answer. For example, isobaric process, W equals P delta V, isochoric 0, isothermal, W equals an RT ln V2 over V1. Before we had moved to QCM problems, an earlier way of asking questions, كنا نطلب من التلميذ إنه يكتب الderivation. يعني if he's going to write it's an isothermal process, he must do W equals integral PdV equals an RT integral dV over V. But now when I'm going to use the QCM questions, no need to derive. You can only write the answer and try to apply. Okay, for students who cannot memorize, they can just derive it where they feel they need to derive it. It's okay if they can't remember the formula, and it's good to know how to derive it. In case you forget, you can remember this way. I've explained the internal energy. I've said that because the particles are in motion, so I cannot study the kinetic and the potential energies of these particles, so I can describe them in terms of some sort of energy called the internal energy, which depends on the parameters of the gas, which are the macroscopic parameters of the gas, which are things that I can measure. They are pressure, volume, and temperature. So we can say that the internal energy, which is the motion of the particles, all this motion, all this vibration, all this collision, all this interaction, repulsion, attraction between each molecules, can be expressed in terms of some sort of energy called the internal energy, okay, which depends on the parameters, the macroscopic parameters that I can already measure. In reality, I cannot measure this internal energy, but I can really measure the variation of this internal energy, how much it varies. I can measure delta U, but I never measure U on its own because it's meaningless. It's the same as gravitational potential energy. So if you're going to take a reference and you're going to measure gravitational potential energy, this potential energy is not an absolute value, it's with respect to a reference. So we're more interested in calculating delta EPG, delta gravitational energy, because we only care how much it increased or decreased its gravitational potential energy. So gravitational potential energy, if you think about it, it's meaningless. It's meaningless if I'm going to calculate just a potential energy on its own. What's meaningful is to calculate the variation of the gravitational potential energy. So here it's the same. The internal energy, it's never calculated on its own. We usually calculate it with respect to a reference or the variation of the internal energy. So for ideal gases, he has found that U depends only on temperature. It only depends on the temperature. So whatever the initial and the final states of the gas were, if we started from T1 and we ended up at T2, we will always get the same variation of internal energy. Okay, so because the internal energy depends on temperature, so if I start from initial temperature T1 and end up with the same temperature T1, so same initial, same final temperature, so my U will not change. So I can say that delta U is equal to 0 in this case, and the variation of the internal energy in case of a cycle is equal to 0. I'm going fast because I have already explained them. Okay, so this is the first law of thermodynamics, which says that the variation of the internal energy is equal to Q minus W. W is the work done by the gas. W external is the work done on the gas. So the work done on the gas is minus work done by the gas, because if you are going just to reverse who's doing the work, you just have to include a minus sign between them. So this is the first law of thermodynamics, which is based on the conservation of energy. I've explained the heat capacities, you all know that. I've derived a formula for delta U, which is NCV delta T. This derivation was based on isochoric process. Although it was based on isochoric process, but this derivation is true for any type of process as long as I am starting from T1 and ending up with T2. Why? Because U only depends on temperature and nothing else. So it doesn't matter what the path I have followed to start from T1 and end up with T2. It only matters that initially I was T1 and I ended up with T2. So this formula NCV delta T is true for all types of processes as long as all processes have the same initial and final temperature. I've explained Meyer's law, which relates Cp with Cv plus R. As you can see, Cp equals Cv plus R, and you can see that Cp is greater than Cv for sure. Remember that Cp is the heat capacity at constant pressure, Cv is the heat capacity at constant volume. So this formula is also important. I've explained the atomicity constant. As you can see, it's a constant which will appear in our equations. It's equal to Cp over Cv. It's always greater than 1. I've related gamma to Cv and Cp. As you can see, Cv is equal to R over gamma minus 1 and Cp equals gamma R over gamma minus 1. So I've passed through the previous slides rapidly. I will complete now with isothermal process. In this slide, I'm going to explain how to deal when we have an isothermal process, how to calculate the work, the heat, and relate points with each other. So let's start first by defining an isothermal process. Remember that it's a process where temperature remains constant. So because temperature remains constant and U depends on temperature, so delta U it's equal to NCV delta T. So for sure du will be equal to 0 simply because du it's equal to NCV dt. So du it's equal to NCV dt. There is no variation in temperature because temperature is constant, so it will be equal to 0. Always in an isothermal process, du it's equal to 0 and delta U also it's equal to 0. So du it's equal to 0 because dt is equal to 0, so we'll get dq equals dw and we will get q equals w. Or we can say that delta U equals Q minus W, and delta U will be equal to 0 because the temperature is constant in an isothermal process, so we will get Q equals W. The heat is equal to the work done by the gas. So the work done by the gas has already been derived earlier, so it's integral PdV from 1 to 2, okay, which is equal to an RT, as it says, an RT ln V2 over V1. So this is in the case of an isothermal process. So you can see that the work done by the gas is equal to the heat supplied to the gas. So Q is equal to W in this case. Remember that for an isothermal process, and if we have an ideal gas and T1 is equal to T2, this will give me for sure back to the ideal gas equation, so PV equals an RT. So I will get here T1, which is equal to P1 V1 over an R. It's equal to P2 V2 over an R. Okay, so an R with an R is cancelled, so I will get P1 V1, it's equal to P2 V2, which is known as Boyle's law. So this is known as Boyle's law. So what is the benefit of this equation? It's if you have a PV graph and you're given P1, for example, and V1, and you are given P2, you can guess V2 this way. So if you know one point, you can guess the other point or other point on this graph if you know one thing about it. For sure, if you have P1 V1, you can calculate T1 using the ideal gas equation. So this equation P1 V1 equals P2 V2, it's used to relate points which are on the same isothermal process. Now let's move to an adiabatic process. You all remember that an adiabatic process has a zero exchange of heat, so Q is equal to 0. Back to the first law of thermodynamics, we have du equals Q minus W. Because Q is equal to 0, then the change in internal energy is equal to minus the work done by the gas. So delta U is equal to minus W. You all know that in an adiabatic process, P, V, and T change. So it's not as in the case of an isochoric process. بالisochoric process we have a constant volume. بالisobaric we have a constant pressure. بالisothermal we have a constant temperature. بينما بالadiabatic process, the P will V with T, they all vary together. So if I'm going to use this equation PV equals an RT والثلاثة عم يتغيروا سوا P وال V وال T. If I have one I can't guess the other. يعني إذا أنا معي ال P مثلا ومع ال V وال T ما بعرفهم I can't guess. بينما هونيك if I have for example if I have P back to the isothermal, if I have only P2 I can guess V2. كيف؟ لأنه T1 is equal to T2 for sure. وإذا أنا معي ال P1 وال V1 I can directly guess V2 and T2. T2 is the same as T1 and V2 is guessed using Boyle's law. Now here in the adiabatic process they will all change altogether. The three of them will change. So there's nothing fixed, no one of them fixed. So if I only know one of them I can guess the other two. Okay, so we will try to find a different relation between PVT instead of this one, which is PV equals nRT, which is useless in the case of an adiabatic process. Or let's not say useless, we can find a much useful relation in the case of an adiabatic process. So let's start deriving this new equation. For an ideal gas, we have seen that for all types of processes, du is equal to NCV dt. Okay, which is equal du, it's equal to NCV dt. This is always, it's equal to minus dW in the case of an adiabatic process, and dW is equal to PdV. So I will get minus PdV equals NCV dt. Okay, let's now differentiate the equation of an ideal gas. PV equals nRT. So let's do a differentiation. So I will start, it's the same as UdV. Yeah, it's the same as the UV, it's U prime V Z V prime U. So it's PdV plus VdP equals nR. They are both constants. They are nothing, there's nothing to differentiate. So we add dt at the end. So in this way we do a differential. It's called a differential. So I've got this form. I'm now going to use equation 1 that I have already derived. And using equation 1, I will try to substitute PdV, this one, I will substitute it with minus NCV dt. As you can see, I've left the rest, so plus VdP plus nR dt. I've left it as it is. لاحظوا هلا بقي معي بالايكويشن I've got dt, dp, dt. So I have only two variables which are dt, dp, dt and dp, yani p and t. So let's arrange. I will get arrange t's together. I will get ncv plus r dt equals vdp. So I will replace cv plus r with cp. So I will get vdp equals ncp dt. So now I will take this equation and redivide it by equation 1. So I will divide this side by minus PdV. رح اقسم هيدي السايد by NCV dt. Okay, because for sure minus PdV it's equal to NCV dt. So I can divide both of them. كل الهدف انه انا بس خلي 2 variables بالايكويشن مش 3. اوكي انا كان باقي معي قبل ال V I will mark it with another color. اوكي هيدا ال V، شفتوا هيدي ال V اللي هون. هلا انا صح كان معي temperature و pressure و temperature بس كمان كان باقي معي ال V. So I have to get rid of this V. أو I have to get rid of the temperature. I have to get rid of one of them and keep 2 only in order to find a relation between only 2. هيدا هو الهدف. For sure the derivation, you shouldn't do the derivation, you should just take the result and use it. So قسمت أنا بهالطريقة بكون طيرت ال dt. Okay, don't forget that Cp over Cv will give me gamma. Okay, dt with dt cancelled and with n cancelled, so this will give me gamma, and I will get minus V over. Look now at this relation. This relation has no temperature. It has no temperature. It has only 2 variables which are V and P. So this is good. We are arriving. So back to the derivation. This equation arranging. So I will replace this one by gamma. Okay, and I will arrange p's to one side and cross multiply. So cross multiplying will give me this one, and then I will divide by p and v to get this form. Arrange it on your own. So arrange p's aside and dv over v aside so that I can integrate easier. Okay, so I'm doing one type of separation of variables. Okay, I'm separating variables each one alone. So now integrating, I will integrate dp over p plus gamma dv over v. If I'm going to integrate, this one will give me ln p plus gamma ln v. Okay, it's constant. Anyway, if it's 0, so the integral of 0 will be constant, so this is a constant. I will take gamma up, بتصير gamma فوق ln v to the power gamma. You all know that ln a plus ln b it's equal to ln ab. So فوت ln ab it's constant. إذا ln pv gamma هو constant هذا بيعني إنه pv gamma هي constant. So for a certain adiabatic process, the PV gamma is a constant. Okay, so I can apply the formula. If I have a certain point 1 and a certain point 2, I can for sure make a relation between these 2 points, which is P1 V1 gamma equals P2 V2 gamma. That's it. يعني إذا أنا معي ال P1 لأول نقطة وال V1 ومعي ال P2 لتاني نقطة I can guess V2 بدون ما احذر التمبريتشر وما بعرف شو. Okay. Once I find T2 V2 I can find T2 لأنه PV equals an RT. Once you find 2 you can find the third. Okay, so this is for a relation between P and V. Now I can do the same and find a relation between T and V and a relation between P and T. I will start first with a relation between T and V. So I will take the result that I have arrived to, which is PV gamma equals constant. PV gamma is equal to constant. I will take this result and I will try to make a relation between T and V. So I will get rid of P, which is pressure. راح استعمل ال ideal gas equation. So P equals an RT, as you can see here. So P equals an RT. I will replace P by its value. So I will get n RT over V, V gamma equals to constant. هلا ال NR هي constant. Okay, gamma وفي هون عندي 1, so I will get n RT V gamma minus 1. So because 1 is in the denominator, so it's down, so I have to write gamma minus 1, which is equal to constant. If n RT V gamma minus 1 is a constant, so for sure T V gamma minus 1 is a constant. So what does that mean? So if you have 2 points on the same adiabatic process, you have the temperature of the first, the volume of the first, the temperature of the second, and you're going to guess the volume of the second, you can use this formula. Okay, so T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 2 for all points in the same adiabatic process. Let's now move to make a relation between P and T. What should I do? I will take the same formula, which is PV gamma equals constant. I will try to substitute P. I will try to substitute V. بدي خلي ال P, بدي أحط محل ال V temperature. I will start to substitute V by N RT over P. So I'm going to substitute this here. بصير في عندي relation ما في بقلبها أبدا volume, في بقلبها بس temperature and pressure. As you can see, بيطلع معي P nRT over P gamma is equal to constant. So this will give me P for sure nR to the power gamma, T to the power gamma over P to the power gamma. So remember that this is to the power 1. So you will get P to the power 1 or P to the power gamma down, you will get P1 minus gamma. So this will be P1 minus gamma. nRT to the power gamma is constant. For sure, nR to the power gamma is for sure constant. So I will get rid of it. It's a constant. So I will get P1 minus gamma. T gamma is a constant. It's written in this way. Or you can do the inverse and say P gamma minus 1, T minus gamma is equal to constant. Both of them are correct. I've only inverted the powers, which means that I have done the reciprocal. Okay, so this is for P and T. You can use any one of them, but the most let's say the most known one is PV gamma equals to constant. So we have 3 equations. These 3 equations characterize a reversible adiabatic process, which are PV gamma is equal to constant, TV gamma minus 1 is equal to constant, P gamma minus 1, T minus gamma is equal to constant. Okay, so these are the equations that characterize an adiabatic process, and they are very important. Now, if you have seen a PV diagram and you see an isothermal and an adiabatic process, you can clearly see that this is an isothermal process. You can see that an adiabatic process is steeper than an isothermal process. يعني دايما بيجي الadiabatic نازل بقوة. Okay, الisothermal أقل. So if you're gonna distinguish between an adiabatic and an isothermal process in a figure, you can distinguish them in this way. You can see that adiabatic process is usually steeper than an isothermal process, and they have usually this shape. Now let's talk about the work done in the case of an adiabatic process. For sure, for all types of processes, work done by the gas it's equal to integral PdV. Because P is variable and V is variable, I can't integrate this way. I have to write it in the form, because I know that PV gamma is constant, so I will write P as constant over V gamma. I will write it this way, dV. Okay, so constant goes out of the integral, and I will get integral V gamma minus 1 dV. So I add plus 1 from up, and I divide by minus gamma plus 1 from 1 to 2. Okay, the constant is equal to PV gamma, so PV gamma is equal to constant, so this constant is equal to PV gamma. So I will multiply PV gamma with V gamma minus 1 plus 1, which will give me V. So it's PV minus gamma plus 1 from 1 to 2, which means that W is equal to P2 V2 minus P1 V1 over 1 minus gamma. This is the work, or you can calculate it simply as the work in the case of an adiabatic process. It's equal to minus delta U, it's equal to minus NCV delta T. You can do both of them are correct. Okay, if you have P2 V2, you can do it like this. If you have already calculated the CV and you have delta T, you can do it like this. But these both relations are the same, simply because P2 V2 it's equal to nRT2, and P1 V1 it's nRT1 over 1 minus gamma. So let's take nR common, so I will get nR delta T over 1 minus gamma, so which will give me minus nR, it's like this, minus nR equals minus nR over gamma minus 1 delta T. Now remember that I have already explained CV. CV is equal to R over gamma minus 1, so this is CV. So you can say that W equals minus N CV delta T. So نفس الفورمولا، يعني هيدي الفورمولا تعطيني هيدي الفورمولا. But when to use each one? For example, if you already have calculated delta U, you can guess the work. Or if you have P2 V2, P1 V1, you can guess work the other way. Both of them are compatible. Okay. Now let's move to an isobaric process. In the case of an isobaric process, the calculation of work is already done. It's P delta V, it's easy. P V2 minus V1. The calculation of heat is also easy, because we have the constant Cp. So Q is simply NCP delta T, where Cp is the constant measured at constant pressure. So these two figures, A and B, the first one, this one, we're moving from large values of V to small values of V. You can see that we have a compression. This is called an isobaric compression. In this isobaric compression, pressure is constant, so PV equals nRT, remember that. So pressure is constant, this one is constant. Remember that when the volume is decreasing, so the temperature will be decreasing. So in this case we have cooling, we have loss of temperature, decrease in temperature. In this case, when the volume is increasing, this is an expansion, and at the same time it's heating because the temperature will be increasing. Okay, so here the temperature will be increasing. For an isobaric expansion, when volume increases at constant pressure, the temperature increases and Q will be positive. So in this case, Q will be positive. That means in the case of an expansion, we're heating, the system will be absorbing heat. The system absorbs heat. If Q is negative, this might not finish, so I have to add, okay, I will add it later. So for an isobaric compression, Q will be negative. That means that we have a decrease in temperature and the system will be producing heat. So it will be giving heat to the environment. In a PV diagram, the curve representing an isobaric process is a horizontal line parallel to the axis. You can see the shape of the curve. It's just a straight line parallel to the axis. So if I'm going to relate any 2 points, for example, this one, it has V final, P final coordinates, and this one, it has V initial, P initial coordinates. Remember that P final and P initial are equal. So if I'm going to relate 2 points, let's assume here we have T initial, and at the end we end up with T final. So we have Charles law, which states that V1 over T1 is equal to V2 over T2. So if you have V1 and T1 for the first point and you have V2 for the second point, you can calculate V2 this way. Where does this formula come from? It simply comes from the equation of state of an ideal gas. Remember that PV equals nRT. It's equal to nRT. So you can see that if I'm going to divide V by T, it will give me V by T. So V over T, it's equal to nR over V. It's equal to nR over P. Okay, it's not writing well. I will rewrite it again. So PV is equal to nRT. I will get V over T. It's equal to nR over P. So you can see that for all points of the same isobaric process, they all have the same N, same R, same P. It's P is constant in the case of an isobaric process. So all points of the an isobaric process will have the same ratio V over T. Okay, so V1 over T1 will give me V2 over T2. Okay, or you can do it this way. So P1 V1 equals nR T1 and P2 V2 equals nR T2. Divide two equations together. Yeah. P with P will be cancelled and R will be cancelled if I'm going to divide them with each other. So I will get V1 over V2 equals T1 over T2, implies V1 over T1 equals V2 over T2. Anyway, they are the same. This is the derivation of this formula. Now let's move to an isochoric process. An isochoric process is the one that is done under constant volume. So in this case, Q, it's equal to NCV delta T. It's always the same, NCV delta T. I can directly calculate Q. You can see all if I have an increase in pressure. So in this case, the temperature will increase. And here I have an isochoric. It's called an isochoric. It's an isochoric heating. So because the temperature is increasing, so in this case Q will be positive and the system will be absorbing heat. So here T will be decreasing, temperature will be decreasing. It is an isochoric cooling, and the temperature will be decreasing, and as you can see the pressure will be decreasing. How did I guess them? Because PV equals nRT for sure. Remember that V is constant, so this one is constant. If the pressure is decreasing, so the temperature will be decreasing, okay, because the volume is constant. So at constant pressure, if the pressure increases, the temperature also increases and Q is positive. This is called isobaric heating. I have to correct. It's an isochoric heating. So I will correct this one, correct it on your, I will correct it later. Isochoric. I'm talking about an isochoric process. If the pressure decreases, the temperature decreases and Q is negative, and this is an isochoric cooling. Okay. In a PV diagram, the curve representing an isochoric process is a vertical line parallel to P axis. As you can see, it's parallel to P axis. At a constant V, we can also apply the Charles law, which states that P1 over T1 is equal to P2 over V2. This time V is constant, so بيطلع معي نفس الفورمula هونيك بس بدون V1 على T1 equals V2 على T2. It will give me P1 على T1 equals P2 على T2. You can use this one to relate any 2 points belonging to the same isochoric process. Okay, so it's derived in the same way. I have derived V1 over T1, but in this case V is constant instead of using P constant. Now let's arrive to the last summary. If you can see the summary, this one summarizes the whole lesson, everything I have said. Okay, we have 4 processes and I have to know how to calculate Q, U, delta U work in each of the cases, and I have to know how to relate my points in each of the cases. Let's start with the first one, which is an isothermal process. In an isothermal process, the temperature is constant. I'm going to read them because I have already explained them. Delta U is equal to 0 on an isothermal process. Temperature is constant. Delta U is 0. Delta U is equal to Q minus W. So delta U 0, Q is equal to W. All the time, Q is equal to work. So if you're going to find Q, you have to find work. So work equals nRT ln V2 over V1, and if you are going to relate 2 points in the case of an isothermal process, you can use Boyle's law, which is P1 V1 equals P2 V2. You can use this one. In an adiabatic process, there is no exchange of heat. Q is equal to 0. Delta U, it's always equals to NCV delta T على طول بحيلا process، بس هون بالايزوثيرمال اصلا delta T is equal to 0. كل مرة هيك delta U is equal to 0. delta U equals Q minus W، بس ال Q 0 بيطلع عندي delta U equals minus W. The work equals P2 V2 minus P1 V1 over 1 minus gamma. مثل ما أنا قلت من شوي I've explained this one. You can either use work equals P2 V2 minus P1 V1 على 1 minus gamma, or you can use work equals minus delta U. Both of them are correct. And if you are going to relate 2 points, you can use P1 V1 to the power gamma equals P2 V2 to the power gamma, or the other 2 formulas which relate P to T and V to P. Okay, but this one is the most used one. Let's go now to isobaric process. The pressure is constant. The same formula for delta U. It's always constant. Delta U, it has always the same formula. I mean, delta U is equal to Q minus W. Work is equal to P delta V, which is nR delta T. Simply, I don't know if I've explained it, but it's P V2 minus V1. So I will get P V2 minus P V1, which will be, P is constant everywhere. So this is nRT, nRT2 minus nRT1. So if you've got T1 and T2, no need to calculate P and V1 and V2. Just write nRT2 minus T1. The Q is always, in the case of an isobaric process, it's Q and Cp delta T, and I can use Charles' law, which is V1 over T, V1 over T1 equals V2 over T2. Now in the case of an isochoric process, V will be constant, delta U is the same formula. Delta U is equal to Q simply because the work will be 0. Remember that the work is the area under the graph. So if you look at an isochoric process, you can see that our graph is a straight line. So the area under it is 0. So there is no area under it. You can see that there is no area. So the work is 0. back. Okay, so I will get Q, it's equal to NCV delta T. So this is Q in the case of an isochoric process, and for sure you can use Charles' law in order to relate 2 points, any 2 points in the same isochoric process 1 and 2. So P1 over T1 equals P2 over T2. Before ending the lecture, I will be solving a couple of questions. I will do problem 24, page 634. This problem says determine the work done on a fluid that expands from I to F as indicated in figure 20.24. What if or how much work is performed on the fluid if it is compressed from F to I along the same path? So he's asking me to find the work done on the gas. أنا علمتكم جيبوا الwork done by the gas, which is the work equals in